Okay, welcome everyone to this continuation of what is tropical geometry. Today I would like to tell you about probably the most important topic in tropical geometry, the tropical varieties. So tropical varieties, algebraic varieties, tropical varieties, again remember or recall that tropical geometry is like mirroring algebraic geometry. And yeah, so let me just remind you about algebraic varieties. So somehow algebraic geometry is about algebraic varieties. Yeah? So if you see my kind of more modern approaches to algebraic geometry, it might be very hidden and you can't really see that anymore. You might look at very different looking objects, but in the end the main motivation is always to study some form of a variety problem. And variety is literally a collection of roots of a polynomial, right? Roots of polynomials. Today I probably will just stay with one polynomial and we'll see the multiple polynomial version kind of later on. But in general, just roots of polynomials collected. And the way I would like to think about it is kind of the standard example of an algebraic variety are the conic sections. So the polynomial as a function in this case is the cone, depending on how it lies in space. And the roots would be cutting it with the plane. This picture is really good. I like it. Of course, I've stolen it, so you can see it. Link in the description. But it's kind of a little bit different from what I have in mind. So in my picture, because I take the roots, I really cut it with the horizontal plane, just the standard plane. Yeah, z equals 0 if you want. And the variety itself moves around. In the pictures, it's the other way around. The variety is fixed, and the hyperplane moves around. Yeah, but anyway, it's kind of the same picture. And all of these are kind of varieties. Here are the kind of the generic ones. If you cut a cone generically with a plane, you either get a parabola, an ellipse, or an hyperbola. Yeah? If you are very lucky, you get a circle. That's literally just cutting it horizontally. And then if you're really unlucky, you get one of the things I don't want to talk about. But anyway, the classical geometric objects, the parabola, the ellipse, the circle, and the hyperbola are examples of algebraic varieties. Right? Algebraic geometry is about algebraic varieties. And I really like this picture, and I like to keep that in mind, that the polynomial defines a function, and we somehow cut that function at a certain point. And yeah, the roots is just a cut with the kind of the standard plane, if you want. And tropical varieties, we would like to define them in the same way. And tropical varieties mimic algebraic varieties. So we have this type of picture. Here's a graph of a tropical polynomial. It's this piecewise linear type thing. Yeah, very, very nice. I can also show you, we'll see another picture momentarily from the book that I'm following, just to pull it up again, just in case. Yeah, so you can get that book. And it's a book I'm following. I'll show you one picture from that in a second, which is a really good one, and I haven't found a better picture than the one I'm going to show you. Anyway, tropical varieties, they should be roots of tropical polynomials. But somehow if you look at this graph and you cut it with a plane, you somehow get the wrong thing. The problem is the thing is already linear, so cutting with a plane is somehow not a good idea in this case. And the whole question boils down to what is actually a tropical root. And I will use this notion tropical root a lot, but it's not a root of a polynomial in the standard sense. It's rather the following idea. Yeah? So root of a polynomial in the following sense. So here's another picture of those. I will come back to that. I call it A. So here's some hyperplanes and this piecewise linear thing. And if you just really think about a piecewise linear function, then it's linear almost everywhere, right? And has some breaking points because it's piecewise linear. And literally the breaking points are the interesting part of the function. Yeah? So maybe we should call the tropical roots exactly the breaking points. So in this picture, it would be, what is a good color now? Maybe black. It would be this thing here, right? So these are the breaking points. And we would like to call that beast a tropical variety, right? With a rough space. Say it again. The interesting part about a piecewise linear function, tropical polynomials are piecewise linear functions, is exactly this type of idea of taking the breaking points And they had a really good picture here that I'm supposed to find at one point, and I think it's this one. So here's a really beautiful picture. Can you zoom in a little bit? That was a bit too much, maybe like that. So here the breaking points, depending on, this is a degree 2 tropical variety, a tropical polynomial. So here you have 2x is like the x squared, 2y is like the y squared, x plus y, remember multiplication is addition here, so x plus y is x times y, here's the linear part and here's a constant part, and this corresponds to all of the breaking points depending on some constants that define the polynomial. So e, d, whatever, and literally the breaking points define then your tropical variety down here, right? Hopefully that makes some sense. So the tropical variety are the breaking points of the function defined by the tropical polynomial. And this is essentially, well, this is how we write it. For one polynomial, you have a function defined by it, and our vanishing set, our variety, v, is all points such that f is not linear at that point. Yeah, it's a breaking point. It's not linear at that point. And this is a tropical variety. You very often read in the literature something like minimum is attained at least twice, instead of what I use here is not linear. That's a good one. And I just think the minimum is attained at least twice is a little bit of a mysterious condition, but kind of looking at the breaking points of a function makes more sense to me, at least. Anyway, just as a warning, it's equivalent if you read somewhere else. The minimum is attained at least twice gives you the same thing, right? But I like to think about it as the breaking points of the piecewise linear function. And yeah, so an example for n equals 3 is this thing. It's kind of very, very strange. So the thing itself is then again piecewise linear in some sense. So it's kind of interesting. Anyway, so I would like to just say what we really do is, okay, look at the definition. I have the function Rn to R, so let's say n is 2. Then I have this function from 2 space to R, which is something like that, right? It goes from a plane and it associates a point in R, so it has some height. But I really only want to look at on the variety in R to the n itself, right? So essentially what I need to do is I need to take my black picture here and flatten it onto the plane. And that's what we really call the algebraic variety. So this thing here, the flattened picture out, that's really what we call the algebraic variety. And again, that's why I like this picture so much. So essentially you take this kind of shadow type object, and that's at the bottom what you call the algebraic variety. So let's just flatten it out. So we'll see a lot of pictures of this type. So here, just really the nice, just whatever, piecewise linear algebraic variety, the roots of the tropical polynomials. Anyway, I hope you enjoyed this video, and I also hope to see you next time.